I'm Ankur, and today I'll be talking about a dynamic Paravirt lock-ops. So I start off talking about the motivation for this feature. Then I'll talk about the state machine for queued spin locks, and then I'll talk about what does switching PV lock-ops, what does that involve? Mostly the requirements and what do we need for safety. And then I'll talk about the patching mechanism, which is breakpoint based, and the the design and implementation of V1, and then the design of the V2 for this feature. So this whole thing started with wanting guests to be more dynamic, and dynamic specifically in the sense that uh, KVM advertises to guests, a KVM host advertises to guests, this feature, whether the vCPUs for the guest are oversubscribed or not. And if they're not, then in quite a lot of respects, it's fairly similar to bare metal, where at least you know that a different process will not schedule out your vCPU. And so if the hint is true, uh, a KVM guest would basically use native PV locks. If it isn't, meaning it is possible that your threads, vCPU threads, can get scheduled out, you use Paravirt PV lock ops, and that's good, except that if this this hint becomes untrue at some point in the lifetime of the guest, um, the host could move to an oversubscribed mode for whatever reason, and the guest has no control over that. Then typically, the guest would see soft lockups. And the recommended fix for this is that a host should only advertise this particular feature, uh, or this particular hint, if it can guarantee the hint for the lifetime of the guest. Now that seems kind of reasonable, but it does seem unsatisfying, given that most of this presentation is about um, switching Paravirt locks, which are based on queued spin locks. Let's go over some of the interfaces involved. So there are 5 interfaces for this, and you can see them, all of them outlined in blue. Interestingly, the one interface which is not a PV lockup is queued spin lock, and that's pretty interesting, and that's a fact that causes a fair amount of trouble when you're talking about switching these, because now you have no way of gating entry um, into the state machine, essentially, right? um, you can gate the PV lock ops, but you cannot gate queued spin lock. For one thing, you don't even know, all the call sites that queued spin lock is called from. So the other notable thing in this state machine is the squiggly lines. So all of the interfaces on the other side of those, that's basically wait, kick. And vCPU is preempted is somewhat special. I'll come to it. But wait and kick are basically no ops for the native case, did, which of course, I mean, makes sense. Um, in KVM, wait is KVM wait. It basically goes and does a halt in the host, and kick essentially it does a KVM hypercall, and it does what you would really expect. So now, having seen the state machine, let's go a little bit into why don't we just use Paravirt locks all the time. Um, so you can see that it, the unlock fast path is different for both of them, and this slide doesn't say which is which, but I'm sure it's easy to guess that the native case, it's just literally a move. The Paravirt case is a locked compare exchange, and if that compare exchange fails, you take the slow path. where you find the next node and kick it. And I mean, clearly they are optimized for different use cases, but you would pay the extra cost of compare exchange even when you don't need it. Okay, another example is that queued spin-lock slow path. It's pessimistic by default for Paravirt. So in the native case, queued spin-lock slow path would spin for a little bit and then queue up if it still hasn't gotten a lock. Paravirt case, the first thing it does is it gets the MCS node in preparation to kind of queue up. All right, now that I've hopefully convinced you on why we need this feature, what does it involve? So fundamentally, what you need to do is you have 5 interfaces. These are spread all over, the kernel modules and so on, and you need to switch all of them atomically. What does actually switching them involve? So this is the example of spin unlock. So you have to transform between the opcodes between one of from one to the other sequence, and of course you might be doing it like multiple times. So the native queued spin unlock, as I think I showed on a previous slide, it's basically a move 3 bytes and a 4-byte no op. The PV queued spin unlock is a call to the actual function which does the queuing, and it's an exchange which is basically a 2-byte no op. The call is interesting because it's a call. Now you imagine a different CPU is doing the patching while one CPU is in the PV queued spin unlock call, and it's called whatever this address might be. When this guy returns the queued spin unlock, when it returns from the call, it returns to address 5, and it expects to execute 6690. However, if you have managed to finish the switching by that point, the contents of address 5 here are 4000. And as you can imagine, that probably will not go very well. And just to belabor the point a little bit more, you might have other ops which similarly go from a call plus no op 2 to just a no op 7 or back. Now, one nice thing is that spinlocks cannot sleep. They could be present for active threads, but they will not be present for sleeping threads. And that's great. All right, so what are the possible active users of spinlocks while we are doing this patching? So it's really the standard suspects. You have tasks, you have software queues, you have interrupt handlers, you have NMI handlers. The only thing which might not be taking spinlock is if it's in a user thread context. Interrupt handlers especially are interesting because the mechanism, which I'll describe a little more in a later slide, is text proc BP, which uses breakpoints. And it's essentially a 3-phased patching process for each call site. And so you would do a write an opcode. After you've finished writing the opcode, you need to synchronize. You need to ensure that all CPU pipelines, they're synchronized. So the caches are synchronized by default. What you have to worry about is the pipeline synchronization, because it's possible that you have the pipeline cache which has prefetched some of these instructions. Maybe they've been decoded into micro-ops and so on. So the IPI is sent out to essentially synchronize the pipeline. And essentially what happens in the IPI is that when the remote CPU receives an IPI, it executes or it will eventually execute an iret, which will make sure that it synchronizes the pipeline such that it fetches the recent, the latest version of instructions written. So IPIs also take spinlocks. So yeah, we need to be kind of prepared for it or handle it in some way. All right, now let's talk a little bit about the mechanism that we'll use for this. So the mechanism is a fairly standard Linux mechanism, which we use for modifying modifying code. There's a typo in that, in the second line. The problem it solves is of patching while potentially executing code that is being patched. And the great thing about this is that it's a single byte instruction. So you know that you can always atomically both write it and execute it. And the way you use it is by replacing the first byte of the sequence that you're modifying by this opcode. It serves as a barrier to entry. The one thing that you do need for that is that this instruction sequence that you are in the process of writing should have just one entry from, it should only be entered from the first byte, from the first byte, which you just replaced with 0xCC. And if this barrier gets hit, the control flow shifts to the int3 handler, and in the int3 handler, based on the address of where this was hit, you know what is the sequence that was supposed to be there, or that that was a PV-lock-op or what have you. So you know what you should emulate now. And PV-lock-ops, they start their life when the kernel boots as indirect calls. So fundamentally, you are really just executing those indirect calls, which are functionally equivalent to the opcodes that were stored here. All right. Now let's talk about what we actually do in V1. So one way of sidestepping, a lot of the difficulties I outlined earlier is basically to use stop machine. So how we use it is basically there's a patching CPU, the CPU patcher, and a bunch of secondary CPUs. All of them essentially work in a lockstep state machine. Interrupts are disabled. You don't need IPIs for a sync core. And you also know that given that you are essentially hogging all the vCPUs, all the CPUs, you know that no PV-lock-ops are on the stack because all other threads are scheduled out and you're not executing any PV-lock-ops. So it's a cowardly way of getting rid of a lot of the difficulties. And the only remaining risk is NMIs. And because NMIs can come, they can so on the primary or the secondary or both. And the NMI handler can then execute a spinlock. So that spinlock, if you're modifying that particular site right then, would end up going to the int3 handler, and you could have a deadlock there. So to avoid that, the int3 handler also needs to implement a subset of the state machine. It essentially, because all CPUs are participating in the state machine, you have to kind of ensure that the state machine keeps moving, and whichever context you are in, whether you're in thread context or in int3 context. And with that, you can make forward progress. If you have multiple NMIs, that complicates matters somewhat, but I won't go into that right now. All right, so this is kind of an example of what the state machine really looks like. Normally you would use IPIs to do some of this. Here, as you can see, the CPU X essentially uh, does SMP con load with acquire semantics to progress to the next stage. Now, what is each stage? So the commented out section actually goes through how the opcodes are really arranged. So the first step is you just patch the int3. That's what the patcher does. It replaces the first byte with int3. It does a local sync, and it's changes some state with release semantics. And all the secondary CPUs, they basically do acquire for that state. So the state would be, say, int3 written. Once they see that essentially int3 has been written, they do the sync. Then you can go and safely the patcher CPU can go and safely write the rest of the state, rest of the opcode bits. And anybody trying to execute this would at this point in time end up in the int3 handler, right? Yeah, so you write the rest of the state. You make sure that the patcher has written it on the secondaries. If it has, you do your sync, and then all that remains is for the patching CPU to write the first byte, which it does, and your iteration is complete. It works. The only problem is this is stop machine, which kind of sucks. And when I sent this to upstream, there was a review comment, which I think in hindsight was pretty understated, which called it Bonghead's crazy code. So now V2. So you want to patch multiple sites atomically, right? Your other CPUs could be executing arbitrary code, including spinlock code. And in any case, patching even a single site is not atomic. There are multiple steps, and each step, even in itself, can get interrupted by an NMI. All right. So the first step is you first introduce a site local barrier everywhere. And what this allows you to do is it allows you to control what executes. So until the site local barrier is everywhere, you just emulate the old code. So once step one is done, you need to introduce a global barrier. And the idea behind the global barrier is that before this barrier, you are only going to be executing old PV-lock-ops. After this barrier, you execute only new ops. The important condition for this barrier is that there should be no spinlocks, and thus no executing PV-lock-ops in the system. And once you have transitioned to the new PV-lock-ops, you're kind of done. All that you need to do is you need to stop emulating. So you go back and replace the int3 that you prefixed with the real opcode. Okay, so most of the work is really in the global barrier. How do we actually get a global barrier when you have multiple vCPUs? Fundamentally, what you need to do is you need to count all spin locks under execution. And the counting needs to happen in the int3 handler, which is good. That's a single point where everything kind of converges. Of course, there is no real way of counting spin locks. Good spin lock is not a PV lock op. So 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 you don't even know where all of them are in the kernel or in the modules. All that you have is what you can get via the int3 handler, which is the rest of the 5 opcodes, not queued spinlock. What's the property that this global barrier holds, essentially? So the barrier itself is pretty simple. You either via RCU or a work queue or something like that, you essentially execute this patch barrier on all CPUs, except for the worker. Let's say this is in work queue context. So at this point, when you're executing this barrier, you know that you don't actually have any locks on that CPU. There are no spin locks in that context on that CPU. So at that point in time, you can switch that CPU to a state where it says, barrier executed, right? And you can essentially act that, this CPU has executed the barrier. And from this point on, this CPU needs to count active lock-ops. Active lock-ops, when it falls to 0, means that there are no ongoing spin locks, let's say, or PV lock-ops really, in the system. And at that point, it's safe to switch. So that's the property in the next line. All CPUs have executed this barrier and no active lock ops in the system. So if the first line is, the first clause is untrue, the barrier CPUs is less than num online CPUs, then you could have active lock ops on, on a bunch of CPUs, but some of them are actually counting these active lockups, some are not. But once this condition is true, you know that all active lockups in the system are actually getting counted. And there are issues here. Spinlock is a really hot path, and so you might have to wait for a long time for this condition to be true. And until then, you would kind of slow down the system. But if the load is too high, you can just abort and you can do things like that. But this condition is sufficient to transition to this new stage. A little more on what we are counting and how we are counting. So first of all, notice what we cannot count. We cannot count the fast path. We have no control over queued spin lock. That does not go through the breakpoint handler. So we cannot count invocations of the fast path. So there can be spin locks executing in the system. You would only see them when they call queued spin unlock. What you can count is the slow path. And the great thing is that the slow path also protects the data structure, because the data structure only gets accessed in the slow path. Or it might get accessed in the unlock if a different CPU has gone through the slow path for the same spin lock. You only really need to be able to tell the difference between the two queued spin unlocks, because one gets executed in the fast path. So you should not be dropping a reference there. But you take a reference in queued spin lock slow path, which you should be dropping in the corresponding queued spin unlock. The one part of data structure that gets accessed is the bit representation, which marks whether this lock is taken or not. And that is constrained to be compatible for both of the spin lock types, because queued spin lock is the same for both of the spin lock types. So queued spin unlock has no choice but to use the same bit representation. And so the only remaining problem is being able to tell the queued spin unlocks apart in both of these cases, and that you do by just keeping some sort of a per CPU bitmap, and that's all there should be to V2. You can find the code here on GitHub. V2 is mostly design documents. V1, you can get the code on GitHub and the patches on LKML. And thanks for attending the talk. If you have any questions, I'll take them. If not, I'm happy to receive them on email, or if you want to collaborate, just drop me an email. All right. Thank you very much.